The newest, most lethal bomber in the United States arsenal wasn't born in a wind tunnel or a manufacturing hangar. Its first iteration was constructed entirely out of code. To understand why, we have to look at its predecessor, the B-2 Spirit. Designed during the Cold War, the B-2 proved that a flying wing could evade radar, but that capability came with deep logistical flaws. Building the B-2 was a massive financial undertaking. The unit cost for a single aircraft hovered around $2 billion, making it so expensive that only 21 were ever produced. Beyond the price tag, the B-2 required constant, meticulous care. Its stealth relied on a delicate radar-absorbent material. A single scratch on that coating could ground the bomber, forcing maintainers to repair it inside specialized, climate-controlled hangars to protect the sensitive materials from moisture and temperature shifts. As adversary air defense systems grew more sophisticated, the military faced a hard limit on the utility of an exquisite, fragile bomber force. The United States needed a replacement capable of defeating modern radar networks, but rugged and affordable enough to field in large numbers. That requirement produced the B-21 Raider. It is classified as a sixth-generation bomber, designed to penetrate advanced air defenses while being as easy to maintain on a flight line as a commercial airline. Relying on the traditional aerospace development cycle of drafting, building physical prototypes, and running iterative physical tests would guarantee cost overruns and decades of delay. This wireframe simulation illustrates the concept of a digital twin. Every component, system, and aerodynamic surface was modeled in a virtual environment long before a single piece of metal was cut in the real world. To create an aircraft that balances absolute stealth with high operational availability, the aerospace industry had to abandon the physical assembly line and perfect the bomber in the virtual realm first. This new approach is called model-based everything. Inside a secure facility known as the Highly Immersive Virtual Environment, or HIVE, developers mapped out the complex software architecture that governs the Raider's systems. Engineers used augmented reality headsets to physically walk through the digital model. This allowed them to inspect routing for hydraulic lines and electrical cables, identifying clearance issues and maintenance bottlenecks while the design was still entirely virtual. Once the code was stable, they moved to a flying testbed phase. The goal was to prove the software worked in the physical world without risking a multi-billion-dollar experimental airframe. They installed the B-21's navigation, communication, and software suites into surrogate commercial aircraft. These proxy planes logged over 1,000 hours of flight time, capturing real-world data and feeding it directly back into the digital twin. Using this commercially inspired software factory drastically streamlined the development pipeline, cutting the time required to certify new software builds by 50%. Because of this exhaustive digital and surrogate testing, the transition to actual hardware was remarkably smooth. During the B-21's first full year of physical flight testing, the aircraft required only a single software change. Looking at this silhouette comparison, the B-21 is notably smaller than its predecessor. The B-2's 172-foot wingspan shrinks to an estimated 140 feet, reducing its gross weight. The B-2's serrated, W-shaped tail is replaced with a single triangle, minimizing edges that return radar signals. Inside, the payload bays are deeper and narrower. Instead of relying on massive rotary launchers to drop conventional bombs, the B-21 uses a modular carriage system designed to deploy next-generation, long-range standoff missiles and bunker busters. The digital twin continues to serve a purpose long after manufacturing. If the Raider's stealth coating gets scratched on the flight line, a maintainer uses a handheld scanner to map the exact dimensions of the damage. That topographic scan data is uploaded directly into the digital twin. The simulation calculates exactly how that specific gouge affects the aircraft's overall radar signature, telling the ground crew whether the plane is safe to fly or if an immediate repair is required. This unbroken feedback loop eliminates human guesswork. By continuously checking physical wear and tear against the digital model, the Air Force ensures the B-21 can operate as a reliable daily flyer. A bomber that flies every day loses its strategic value if its core technology becomes obsolete by the time it enters mass production. This diagram shows the Raider's Open Mission Systems architecture, called DevStar. Physical hardware is entirely decoupled from software. Unlike legacy aircraft requiring years in a depot for upgrades, The B-21 receives rapid, over-the-air software updates, integrating new logic much like a smartphone. This open architecture ensures that as new threats emerge, or as new tools like hypersonic weapons and collaborative drone swarms are developed, the radar can be updated to control or counter them in a matter of months rather than years. The logical conclusion of this deeply integrated software is autonomous flight. The B-21 is the world's first optionally crewed strategic bomber, engineered from the ground up with the necessary architecture to execute strike missions entirely without human pilots on board. It demonstrates that sixth-generation air superiority relies heavily on the code processing data behind the scenes, rather than just the physical shape of the airframe. As the B-21 Raider begins replacing the United States' aging bomber fleet, its autonomous capabilities raise a lingering question. This is the first bomber built to fly itself, and it may well be the last one designed with a cockpit.